Good evening, everyone. Thank you for coming. I have a short introduction. We've got a long introduction for me. So firstly, I would like to thank Teo Cruz, who's at the back there, who is our AV guru and makes excellent films of all the talks. They are available online. There's about 80 of them, 80 plus of them, on a YouTube channel, and I will send you the link. It is on the bottom of all those messages I send you, whatever. So yeah, have a look at those, and thank you, Teo. So you can binge watch those over Christmas. That'd be fun for you. Okay, so I first met Pete Silver almost 35 years ago. I worked out this morning or yesterday. It's so long ago that Pete had a full head of hair, believe it or not. Sorry, Pete. And I still had a sense of humour back then. Pete Silver had been studying with John and Julia Frazer at the Architectural Association, and I think perhaps a bit more of that later, that Pete might touch on that. Pages of this. Anyway, we ended up meeting as architectural experts, and apologies if anyone's heard this story before 100 times. We ended up meeting as architectural experts on a morning TV show. That's how interesting TV was in those days. Discussing the merits, or otherwise, in brackets, of the architectural opinions of Prince, now King Charles. Boo. Anyhow, afterwards we became very good. We've become great friends. We've remained friends ever since. We've never had an argument. And we have taught together. In fact, it was Pete who got me into teaching, so you could thank him for that or not. And we have had a lot of fun. And I've co-authored 6 books in the meantime, with the latest one out in January. January? What kind of time is that? In time for the sales. Anyway, to discuss this evening, artificial intelligence, what is it, and why not? No, not why not, why now? Even.
Why now?
Why
bother?
Why not?
Why bother?
Sorry. I give you Pete Silver. Thank you.
Thank you, Will. Thank you, Will. Thank you so much for coming. It's just nice to have you guys here, and you guys are the future. Nobody else in this place is. Just you now, and me, and us. Hopefully. Okay. I'm going to read today, and those of you who know me know that I don't usually read from text, but this is a kind of a one-off lecture, so I'm going to be reading a lot, and I apologize for that. But also, I know that I'm going to be fact-checked, particularly by the computer scientists who are all online watching this and going, "Well, let's make sure Silver gets his facts right." So I apologize in advance for reading a bit, actually quite a lot. You must quite rightly be thinking, God, not another talk on AI, because those of you who've been here this term should have heard quite a few discussions on AI. I don't know if you've attended them or not, because lots of people have already beaten me to it. And I have to say a thanks to Gunther and to Lindsay for organizing these lectures. And we've had some fascinating insights into the thinking. Nevertheless, I'll try to entertain you and address some of the issues that have already been brought up by our colleagues and others. Okay. And I'm going to do what, excuse me, most of the people that have talked about AI already do, which is delve a little bit into the history of how we got to where we are today. I'm going to do it a little bit more depth, I think, or I hope. I think it's important because it's cultural context. And they're going, wait a minute, this is a tech lecture. No, it's not, because every lecture that we give, whether it's technical or culture or anything else, it always envelops everything. We can't possibly talk about technology without talking about history. We can't talk about history without talking about technology. So just a point to mention. So here we go. Excuse me. And I'll try and move quite quickly through this. So this is, some people say the abacus is the first sort of computational machine, which is fair enough, but most people will consider that Blaise Pascal's box, this astonishing box, is the first, excuse me, mechanical calculator, first true mechanical calculator. So this is, I think it says there, 1642. What it does, apparently, is it has these carry mechanisms which adds 1 to 9 on one dial and carries 1 to the next dial when the first dial changes from 9 to 0. So that's a fantastic achievement. And, you know, as an architect, we're architects, I think most of us in this room, I'm fascinated, apart from anything else, by this incredible transformation of calculation into a three-dimensional mechanical device that did that job. That's an astonishing thought process to begin with. You know, on the one hand, you've got loads of numbers. On the other hand, you have, these are his drawings, Pascal's drawing. And Leibniz is another guy, Gottfried Leibniz developed this machine. And in those days, in 1600s, they were mathematicians, they were engineers, they were also philosophers. Both Leibniz and Pascal wrote philosophical, very interesting philosophical treatises. So this is 150 years later, but it's an invention that was become a critical conceptual precursor to the development of computer programming, because it's a loom. It was invented by Joseph Marie Jacquard, and it changed the process of manufacturing complex pattern textiles by using cards with punched holes to change the patterns. And each row of holes corresponded to one row of the design. So this is the beginning of software, isn't it? So the ability to change the pattern of the loom's weave by simply changing the cards had all sorts of applications, because the patterns of holes in punch cards can represent any kind of data, can't it? And then can be used to store the data. So believe it or not, up until the 1970s, this was still the main way that we inputted data into computers. I was working with computers without screens in about 1974. It's the very first time I was using them. And we were still inputting data this way with punch cards. So, you know, well done, Monsieur Jacquard. Francois here, it's a bad translation, but well done. Fantastic. Am I doing something wrong? Oh, sorry. It's got a mind of its own. Some AI is controlling that fucking thing. Not long after Jacquard's invention, as some of you know, Charles Babbage proposed the idea of a calculator that employed what we know, mathematicians know as divided differences, a difference engine, which then evolved into this analytical engine. Now, many consider this extraordinary machine to be the first fully automatic, and in other words, reprogrammable mechanical calculator. And if the Pascaline box was astonishing, as an architect, again, this is even more so. Absolutely astonishing piece of kit. And to the aficionados present or online, you computer scientists up there, it's also known as for being Turing complete. You'll know what I mean by that. It's a Turing complete device. Whoops. What happened during the First and Second World War was that there was a great need for secrecy and communication. So encryption and decryption of secret messages became absolutely critical. So two things happened. On the one hand side, that became very important, and on the other hand side, electrics started to influence the way computers were designed, or calculators were designed, I should say. So the First and Second World Wars are very important. You probably already know this. The Enigma machines, this is it's a family of machines. There wasn't one Enigma machine, it was a group of machines. It was invented by a German engineer, Arthur Scherbius. And it consists of a keyboard, as you can say, which is coupled to components that could rotate disks in tiny steps. Like we use stepper motors nowadays to do that, controlling digitally tiny steps. And each key press could then result in a different mechanical configuration. Now, fortunately, at the same time, a British script analyst by the name of Bill Tutt, who was working in, where was he working? I can't remember anyway. He discovered that the key stream produced by the Enigma machines, it displayed a statistical bias. Okay, it deviated from random, and that these biases could be used to break the cipher. So what we needed then was another computer to deal with that. And that computer was this one. It was called the Bomba, which was a Polish word, bomba. And this was designed by Alan Turing, who some of you will have heard of, with mathematician Gordon Weichman. And it was developed at UK Bletchley Park, which some of you might have heard of, which is the British government's Code and Cipher School, which is now a museum, which I highly recommend you visit. That's on display there. The next generation, so there's a lot of toing and froing going on here. The Enigma machine's invented, then Turing invents something to crack those codes, and then the Germans do something. So the next generation of teleprinter messages was an Enigma machine known as the Lorentz cipher. And again, an English engineer called Tommy Flowers, who was working in North London, Dollis Hill, at the Post Office Research Station around 1943. He designed Colossus, which many people do consider to be the precursor of all modern computers. Truly programmable, if you like. Electronic digital computing. So that's key to where we are now. Just a short jump into this critical thing about analog to digital. I'm not going to go into a lot of detail about this, but suffice to say that what really completed the transition from A to D, as we call it now, was a result of the work by George Boole. But that was how long ago was that? 19th century, some way back. Boolean algebra laid the foundation for the logic systems that lie at the heart of all modern computing. And the logic functions that we now use in integrated circuits were all Boolean logic, and he basically invented logic gates. So what we do now, as you all know, I'm sure, is we use binary logic. We've turned everything into truth and lie, on and off, yes, no, very simple, ones and zeros. That's, an analog wave, continuous information broken down into bytes that we can then take and push through gates to solve problems. So nothing's changed since that principle in terms of how we do computing. That's still at the heart of basically all computing. This is what we're here to talk about. Excuse me, I need a drink. Can we cut that when we... Anyway, yeah. Bearing in mind that it's all logic gates and ones and zeros, as computers evolved, the philosophy of artificial intelligence became a branch of the philosophy of mind and the philosophy of computer science in order to pose questions like this. And this was happening a long, long time ago in terms of your lifetimes. Back in the last century, quite early in the last century, these are the questions that were being posed. I'm not going to read them out. You can read, I think, I hope. You had a reading week not a while ago, so... Yeah. They are critical because when we're exploring the concept of artificial intelligence now, these questions should come up time and time again. Okay. Some of you will have heard of this. The Turing test was introduced by Alan Turing, his 1950s paper, Computing Machinery and Intelligence, which opens with the words, "I propose to consider the question, can machines think?" Turing proposed that an evaluator would judge conversations between a human and a machine, whilst being aware that one of the two partners was a machine. And that if the evaluator was not able to tell the machine from the human, the machine would be said to have passed the Turing test. The test result would not depend, and this is quite important too, on the machine's ability to give correct answers. This is what Turing said. People forget this. Only on how closely its answers resembled those that humans might give. Now, this is another topic which I'll come back to. Because thinking, so his question, can machines think? Because thinking was actually quite hard to define, it still is quite hard to define, Turing rewrote the test as, he called it the imitation game, in which an interrogator asks questions of a man and a woman in another room in order to determine the correct sex of the two players. So, Turing's imitation game is actually cleverer than it may at first seem. It does not rely upon a huge factual database of information. Of data, I should say, or expert database, rather on an understanding of human sexual dimorphism, and hence an ability to demonstrate emotional sensibilities such as empathy and aesthetics. Turing, by the way, was gay, gay himself, which only adds to the complexity and intrigue in all of this. But I think that's critical when we later we'll find out that when trying to, if you like, agree a definition of artificial intelligence, that definition, that the right Turing test was used, shall we say. Kind of important, I think. Anyway. Either way, it soon became clear that critical to the philosophy of AI was the definition of intelligence, which in turn was linked inexorably to the definition of the mind and of consciousness itself. Of course, such questions predate Turing and others, forever, if you like. People have all been asking these questions. One thing is in particular of the dualist view of the mind as being non-physical, therefore not bound by physical laws that govern the body. And I think Sigmund Freud sort of put it quite well with this statement here. It's water. Thank you. I think he's indicating that I might be sounding a bit croaky, I think. So, in some of the lectures, a number of lectures I've heard this year about AI, there's debate. There's a very interesting. The debate is over intelligence and grammar, the relationship between the two. Yes. Apparently, it's settled because both humans and machines have an innate sense of syntax. But as far back as 1637, René Descartes, his discourse on method, noted that although automata, more of them later, are capable of responding to human interactions, such automata cannot respond appropriately to things said in their presence in the way that any human would, okay, or can. Again, this is to quote another well-known contemporary philosopher. I mean, it's fairly dogmatic, but it's saying the same thing that René Descartes said back in the 1600s, I think. Yeah. This is semantics. Even the highly intelligent Samir had to look twice at this before he realized. I showed him this, before he went, oh yeah, okay, I get that. Computers can't deal with this. AI can't deal with this. It's an English language thing, so some of you who are not English might have to think about this for a little bit. And funny, on this topic, just to let you know, so-called AI has a real problem with cryptic crosswords. And in the recent final of the Times crossword puzzle, the Crossword Genius app, AI app, crashed with 5 clues unanswered and 2 wrong guesses. Not good. Not good. So, again, a number of lectures already have alluded to this particular event in the early 1950s. Not long after Turing's paper was published, various names for the field of thinking machines arose, including cybernetics, automata theory, and in 1955, John McCarthy, who was a professor of maths at Dartmouth College, USA, decided to organize a group to clarify ideas about thinking machines. And this became known as the Dartmouth Workshop. Took place in the summer of 1956, was widely considered to be the founding event of AI as a field of study. When you read about this online, it will say the founding event of AI, not the founding event of AI as a field of study. That's my addition. I think it's quite important, frankly. Anyway, McCarthy apparently picked the name artificial intelligence partly to distance the association of thinking machines with cybernetics and automata and link it more closely to information theory. So, let's get to cybernetics. This field that John McCarthy tried so hard to ignore had a very particular view of intelligence. Specifically, as a result of some of you will know, Norbert Wiener, his basic philosophy of cybernetics, he called it the science of control and communication in the animal and the machine. So while the study of AI was gaining funding and prominence, cybernetic sciences, such as the study of artificial neural networks, which didn't come under the AI thing, were downplayed. But what happened in the 1960s was that cybernetics began to develop important cultural traction, if you like, through exchange with the creative arts, with design, even architecture. Notably, the Cybernetic Serendipity exhibition, which was at the ICA 1968, which was curated by Jascha Reichart, who has lectured in this series at this university, and the Fun Palace Project, where the cybernetician Gordon Pask was consultant to Cedric Price, who's also lectured in this series, and the theatre director Joan Littlewood. So you're in the right place. So here's Gordon with the universal constructor. This is a model of flows of data. It might still be considered to be one of the only truly three-dimensional computer screen ever built. Your screens are all flat. Everything you look at is flat. This is truly three-dimensional. All the data that's flowing around here is literally in 3 dimensions. Excuse me. This was designed and built by John and Julia Frazer and their students at the AA in 1990. Now, Gordon Pask taught at the AA, and he made it known to his students that he was critical, even then, of certain interpretations of artificial intelligence. Gordon argued that from a cybernetic perspective, intelligence resides in interaction, not inside a head or a box. The emphasis for Pask, according to his colleague Paul Pangaro, was that human intellectual activity existed as a kind of resonance that looped from a human individual through an environment or apparatus back to the individual. Gordon also gave us this important statement, which again, a lot of the people that I've heard talk about artificial intelligence, they talk about knowledge as if knowledge, is just like there somehow. But Gordon always used to say, he gave us those 3 statements, but he also said to turn data into information, if you're a teacher, that's your job as a teacher. Loads of stuff out there, loads of data. Teacher's job, turn data into information. Student's job, turn information into knowledge. You digest it. It's up to you if you can make that second connection. I always found that fascinating. Here, let's see if we can watch information, data flow. We could animate this. What you're looking at, this particular example, is a cellular automata, which I'll talk about in a minute, but we could animate this 3-dimensionally, these cubes, so that you could literally produce a three-dimensional, a true three-dimensional image just with the LEDs, with light-emitting diodes. Okay. Where am I? Back to where we were. So why has this idea, or this phrase, AI, been so successful in self-replicating in recent times? Why have we embraced artificial intelligence without questioning what it meant or what it means in the first place? So in June 2022, the Google language model for dialogue applications, LaMDA, not to be confused with the London Academy of Music and Dramatic Arts. They must be really pissed about that. Their chatbot received widespread coverage regarding claims about it having achieved sentience, i.e. being conscious. Initially in an article in The Economist magazine, 2022, not that long ago, a Google research fellow said that the chatbot had demonstrated a degree of understanding of social relationships. And later, a Google engineer claimed in an interview with the Washington Post that LaMDA had achieved consciousness. These assertions were roundly rejected by experts throughout the world, and the researcher was placed on leave by Google. So that should have been the end of it. But of course, it wasn't, because everybody got nervous. When I say everybody, I mean people who stand on stages with jeans and T-shirts and look evangelistic type people. I shouldn't have said that, should I? Make sure that's cut from them. Cut that from them. Not to be outdone, OpenAI's chatbot, ChatGPT, was released around 6 months later So the fact that the original LAMDA model was rejected by an awful lot of people made no difference whatsoever, because it was like the cat had come out the bag, I suppose you'd say. So ChatGPT was released 6 months later, and that was promoted with an article in Nature magazine, another well-respected magazine, by researchers at Stanford University who asserted that ChatGPT broke the Turing test. Which Turing test did it break? The original, the first one, the one that Turing then rejected, by the way. Not to be outdone, another evangelistic guy with a T-shirt. Shouldn't say that. Don't keep saying things like that. Oh, another one. Shit. Interestingly, we were informed at one of this term's AI lectures that ChatGPT, etc., were such game changers that Meta's current AI spend is around $190 billion per annum. So this figure apparently gives an indication of the current importance of this type of software to the world. So this is them saying, we're going to spend $190 billion to make the world a better place. And, it's got nothing whatsoever to do with profitability, has it? Why did folks start to adopt the phrase Gen AI? Happened in this university, was it last term or this time? I'm not sure it was last year, when suddenly all the emails no longer had AI, they suddenly had Gen AI. It wasn't called AI anymore. Somebody decided, somewhere down the line, to call it Gen AI. I wondered if they realized that AI on its own was indeed a misnomer, and therefore felt the need to backtrack. So what exactly is generative AI? Sorry, you don't have to, I'm going to answer, it's okay. If there's such a thing as generative artificial intelligence, what exactly would generative intelligence be if it wasn't artificial? Generative intelligence. Does that make any sense? Similarly, what was AI without the gen? It's a bit like Strictly Come Dancing, isn't it? I mean, it's a nonsense, grammatically nonsense, frankly. So I'm worried about that. But just to, excuse me, sorry about this. Just in case it does have any bearing on artificial intelligence, let's have a little look at the evolution of generative computing, shall we? Starting with feedback, because it's critical to all kinds of generative computing. This is called a flyball governor, used in various forms in the 17th century. It's a centrifugal governor, and it was developed as a very elegant solution to the problem of balancing locomotive engines. So if a locomotive engine is going at a certain speed, suddenly it goes down a hill, the wheels are turning faster than the engine. And the engines used to basically blow up. So what you have to do is reduce the amount of petrol that's going, or fuel that's going into the engine, steam, sorry, not petrol, steam in those days. And the flyball spins as it accelerates, lifts the valve, and reduces the amount of steam going into the thing. Very, very elegant feedback system. Okay, that's the beginning of it. Here's some more examples. This is video feedback. It'll be familiar to those of you old enough to remember the original Doctor Who series. Maybe not. It's the result of a little bit of noise when a camera, basically you put a camera looking at its own screen, filming itself. And to begin with, there's nothing at all. But any kind of little bit of noise or grit in the system starts to feed back on itself. And then it becomes controllable. It's a very interesting process. Video feedback. In computer science, tabula rasa, T-A-B-U-L-A-R-A-S-A, Latin, it refers to the development, I'm sorry, this is still part of this feedback thing, of autonomous agents which are provided with a mechanism to reason and plan towards their goal, but no built-in knowledge base, okay, of their environment. So tabula rasa means in Latin a blank slate, okay, there's nothing. So in nature, all of the things you're looking at here, termite mounds, swarms of bees, flocks, are all examples of where in nature self-organization happens. If you like, emergent intelligence happens all on its own. Cybernetics, automata theory, all these things were very interested in this way of understanding intelligence. How does it naturally evolve, if you like? Shoals of fish, all examples of self-organizing systems. This was back in the noughties. It's a design studio in this building, run by John Goodburn, Will McLean, and myself. We decided to explore the concept of tabula rasa, and we built our own autonomous agents. So these little robots are they're little motors and 3 wheels, and one of the wheels is a roving wheel, freewheel that can go in any direction. And it's got a very simple feedback system. It's got a sensor inside. It's a sound sensor. All it does is the moment it hears something, like bashes into something, it hears something, it reverses the engine, forward and back. That's it. It's the only rule. So we thought we'll build some, and we'll see if they, begin to develop some behavior. We'll watch them and see. This poor chap, he's trying to get everyone else to move, but they're not interested, are they? Hey! Fantastic. Oh, didn't mean to do that. Help, Teo, get me out of this mess. Okay. That was a lot of fun. I'm not sure that we learned an awful lot by building those robots, but at least we began to think, okay, something might emerge, and if we kept going, something might have emerged. This is a similar vein, and this is, again, a quest to generate emergent behavior artificially. Some of you might have known these cellular automata systems. So this is in the 1950s. Stanislav Ulam and John von Neumann, they invented a rule-based system that would generate patterns on a grid, a method for calculating sort of a liquid motion was what they considered it to be, by considering liquid as a group of discrete units. So you've got an irregular array of cells, which can be any number or dimensions, each having 2 states, again, on or off. Each successive generation, a transition rule is applied to determine the state of every cell in relation to those in its intermediate neighborhood. E.g., 8 cells, regular 2-dimensional grid, 256 possible states. So if you play this, of course, again, a little bit like what we were trying to do with the vehicles in the earlier demonstration, if you play it on a kitchen floor with dinner plates, you don't see a lot of emergence, but in the 70s, 1970s, John Conway, he used the computer to generate, to design a cellular automata. He called it the game of life. And after many generations, different patterns did begin to emerge, according to how and how many cells were originally placed on the grid. And as in nature, what the game began to illustrate, the more and more they used it, was how very simple rules, and this is what happens in nature, develop hugely complex systems from a very simple starting point. So that's cellular automata. Sorry, I've just jumped. Oh, no, I haven't. I've lost something, but never mind. I lost a slide. I'll talk about it instead. Ignore what's on the wall for a moment, because I have to talk just quickly about neural network computing, which came after the cellular automata. So this was in the 1980s, working out of Imperial College. Igor Alexander developed the first, what would you call it? It was a neural pattern recognition system. It was known as the Viz. Some of you might have come across it. It was a system, a bit like you would think you would use AI to do today, that could recognize a facial expression. It learnt to recognize a facial expression. He designed a computer to do that. He called it Yorick, after the Shakespearean, skull. And we were very privileged to visit Igor at Imperial College at the time when they were working with Yorick. And Yorick was beginning to, it was, an early, if you like, learning software. And Igor showed, a bit like the Universal Constructor, Yorick was a computer which had lots of LEDs flashing all the time. And Igor said to us, it's interesting because when it's not being fed information, they would feed them faces, very obviously smiling or frowning or whatever, and it would gradually learn what a smile or a frown was, so it could answer that question. But he said sometimes there'd be nothing, no input, and then the LEDs would start flashing suddenly. And he said he thought it was dreaming. He thought the computer was processing information. You could see that, because like the Universal Constructor, the whole idea was that it would reveal that data was moving. So the thing was sort of somehow working on its own, which we found very interesting. So what you're looking at now, sorry, this is bimorphs. The evolutionary biologist Richard Dawkins designed this program to emulate evolution. It's a generative computer program illustrating basically the power of natural selection. So it was a simple 2D branching system, symmetry rules, because most of the world is, in nature is symmetrical, funny enough. As John Frazer always used to say, two of everything down the outside and one of everything down the middle. That's pretty common in nature. So this is Richard Dawkins' branching system. So he was he thought you could breed through the computer families of insect-like forms, and he called them biomorphs. So, if a machine can learn, surely it can generate outputs in the same way as evolution works. So, we get back to the idea of the genetic algorithm. Again, this is not what's known as AI at the moment. This is something that engineers have been using for quite a long time. Optimization. You can breed a better turbine blade, possibly. Okay. In the 1990s, this is from John Frazer's book, An Evolutionary Architecture. This illustration is John Frazer and Peter Graham. It's a 1993 into the evolving Tuscan columns by genetic algorithm for a better fit, if you like. So architects have been using these systems for quite a long time. I have to mention this because that last image came from this publication, An Evolutionary Architecture, because it hasn't been mentioned in any of the contexts of AI in all the lectures I've heard this term or even last year. We are architects. We have been involved in this world. And I just want to kind of emphasize this, because again, this is back in the last century, end of the last century, but still. So this is John Frazer's book. At the very least, I recommend you read Gordon Pask's foreword to this, to evolutionary architecture. You can access it online through the AA. It's free. Oh, gosh. Will mentioned hair. I had some in. So Gordon Pask was affiliated to the Architectural Association in the 80s and 90s, possibly even earlier. I'm not sure. It might have been. Along with John and Julia Frazer, Ranulph Granville, Paul Coates, and others, and under the encouragement of the chairman at the time, Alvin Boyarsky, this group pioneered the application of cybernetics and machine learning to architecture, and specifically through the work of John Frazer's diploma unit from 1989 to 1995. That's the class of 1990 that you're looking at there, just to keep that link to architecture. So back to today. Where are we? Apparently, the world's most powerful computer is powered by 1,152 neuromorphic processors and comprises 1.15 billion artificial neurons and 128 billion artificial synapses distributed over 140,544 processing cores. And it can make 20 quadrillion operations per second. You think that's fast? 20 quadrillion operations per second? It's not even close to what you can do. Not even close. Recent research on the human brain estimates that 1 cubic millimeter speck of brain tissue, that's about 1/millionth of a whole brain, is composed of roughly 57,000 cells and 150 million neural connections, giving the whole brain roughly 150,000 billion synapses. So luckily, you're way more intelligent than any AI program that currently pretends to exist. Okay. I'm coming to the end. I've heard a lot of lectures on AI, and they always end up with things like, this is a warning or a message. This is not a warning or a message. Just a conversation that ends with a question. And here it is. Machines can employ feedback. We know that. They can learn. We know that. They can optimize information. We know that. They can even predict. But you have to ask, does any of this make them intelligent? And I've got a little anecdote here. In one of the early short stories of that great science fiction writer, Isaac Asimov, it's called The Last Question, which apparently was his favorite story. Asimov postulates that mankind discovers immortality and hyperspace travel, and hence ends up populating the entire universe by the time it is dying, and all the suns are turning into white dwarfs. By then, mankind becomes a single discorporate mind that is linked to a single discorporate computer. The computer has, for billions of years, been asked periodically the same question. Can entropy be reversed? Each time the computer replied, inadequate data to give a meaningful response. When the question was asked by the last dying single discorporate mind, the computer gave the same response, but it then continued to think about it after mankind had died out. And when it finally crunched all of its billions of years' worth of accumulated data, it announced, "Let there be light." Thank you very much. Good night, I should say.